Good evening to all of you, and wherever you are in the different parts of the world, very warm welcome. And really thankful to the organizing group, Chief J Potsdam Group, for this inviting me to this seminar series, and let me present our work in front of you. Whatever I am going to present today, this is something we talk about a lot, but we don't go much deeper into real life case studies because there are not very good examples, at least good examples we worked or we came up across. So therefore, whatever I'm going to talk about based on some observation we made, and this is all published. So this is all published. So whatever I'm going to present today, it is from our publications or some publications. So there is no disclosure is required for this kind of for these materials. And what I'm really interested to talk before going into my talk, just give me a brief of myself. Although I'm working, I'm a structural geologist by profession, but 20 years I'm working for the industry only. So I really don't get much time these days to go into research because of my other priorities, but that is my core expertise and that is where I belong to. So that is always I do, and that's my first love. So, and I'm currently working for hydrocarbon exploration company, but my portfolio is right now into geothermal. So I'm still working on learning on that subject. So that's a brief about me. So whatever the key questions today we have. So what is the role of increasing magma processes? Sorry for the typo there. So one I is missing. And during the progressive rift evolution. And this transition, we always hear about active rift, passive rift, but how they interplay. And present day, due to many works, we know that there is no clear-cut active or passive rift. We are looking for any kind of a successful rift. But the when and how the transition is happening and where these thermal buoyancy forces came into picture at what point of time, that is still we think that is still a part of research. And when there is a change in these thermal boundary conditions, what kind of changes we do see in our rift morphology? That is a very interesting observations we made, and that is one of the factor we do see that may create some rift asymmetry. This kind of thermal buoyancy forces at different stages of the rift. So with this, let us come into this picture. This is a very well-known published picture from Manashal's group. And we know that how a successful rift occurs or happens throughout the time and space. So it starts with stretching with broad distributed strain with some, then it focuses focus drifting during this necking phase. Then when there is a coupling between overlying upper crust and underlying mantle, that little coupling. So then we see this coupled domain hyperextension, and that leads to exhumation of the lithospheric mantle. So that there we see the exhumation part. And then it starts with some early oceanization, and then it finally a successful rift goes into seafloor spreading. With the initiation of seafloor spreading, that complete cycle is over. So this is what, if you see anywhere, it is a progressive thing. We can see stage by stage, one by one. But instead of that, probably I like this kind of a diagram. This is the same group of author working later on, because this is not just a one stage by stage vertical stacking. It is just like stratigraphic Walther's law. It happens laterally also. So you can see some of the how it started with the stretching, then several focus strain localization or happens at several places, but that doesn't mean that everywhere it will create a successful rift here. So some of them gets aborted and some of them undergoes successful rifting. So whatever we have this kind of situation, these are probably a kind of frozen in time sections where we can see this effect or behavior, that how the stretching to that thinning or exhumation phases goes into. So that is one of the keen observation we made, and our observations are mostly based on seismic sections and some gravity magnetics. So you used 3D seismic sections. We use a lot of well data also to constrain our timing. And obviously, we do have some background gravity and magnetic studies. So whatever I'll talk about today about this, some glimpse, because I was told by Kim earlier that we have to give some, because I'm presenting not a generalized topic, a very kind of local observations at some point at some part of our world. So I'll little bit talk about this East India evolution of the East India passive margin. We'll talk about some crustal architecture of the failed Kaveri reef zone. So that is whatever we are discussing. Kaveri was one of the part of the reef. And then obviously we talk about the main topic, that is the interplay of stretching buoyancy forces during this evolution. So just give you a quick brief that how India and Antarctica evolved. This is some kind of plate tectonic snapshots, but these snapshots are not a rigid plate or a fixed plate uh, reconstructions, because we do follow a separate reconstruction model, which generally tight fit reconstruction doesn't involve that exhumation and other parts. So we try to see everything together, we put it together in our own method, but that's, I'm not going into that. We do have a separate, although it can be a separate presentation. So what I can say that there are the rifting started since Jurassic. So these are the remnants of Jurassic rifts over here. So as it progressed, we'll focus on this part only. This is the Kaveri rift. But to understand Kaveri rift, we have to understand this rift. This is called KG rift. So KG rift also initiated in Jurassic together with Kaveri. But once it happened during this part of during this phase, that 132 million year, East India passive margin underwent actually two breakups. The first breakup happened between this part, India and Antarctica, where microcontinent Elan Bank, which is right now is a part of Kerguelen Plateau, was still attached to India. And then it happened between 132 and 123 million year. There is a rift jump happened. So there was a renewed rifting initiated between East India and Elan Bank, and Elan Bank is slowly transferred to the Antarctic plate and it moved away. So, and this, this transition happened through a dextral transform system, that is we call Coromundal transform system. I will talk about that also. So this Elan Bank has moved along this, and if you can see that it moved along this trajectory, and it cut across the older Kaveri rift. So that's what the Kaveri rift becomes a very complex rift system. So if you can see that, if I zoom into this part again, and so this is the KG rift, this is Kaveri rift, and this is the Coromundal dextral transform zone, which accommodates these two rift, and it also controls the breakup as well as the lateral clearance along this margin, okay, to got away to the other part of the plate boundary. So the Elan Bank probably would have been sitting here, and it moved away along this path. So whatever we are focusing in this region. So you can understand that this region initially underwent extension, and then it underwent some transform readjustment during its evolutionary phase. So that makes this basin very complex, and the observations are very complex, and still we are making new observations, and we'll try to publish that. But it is not that this study is the end of the study. Obviously, we cannot say that, but there are a lot of complexities are coming in. So we'll try to focus on some of the complexities that is related to stretching and buoyancy. So if you see that this is the Kaveri rift, this was the initial extension, and then it was the accommodation in this region. So whatever we'll talk about few profiles. I cannot discuss all the profiles because of the timing constraint, but obviously the publication is there, so we can always refer back to that. So what we see here, if we consider that this part is one of the, probably this is, if you can relate to that, this kind of continental ribbon, the breakup happened in between India and Antarctica. Breakup happened to toward the southeast of this feature. This is called Karaikal High. So we may correlate with that. It may not be a one-to-one correlation, but just for bringing all of you to the same page that what we are thinking. So this probably will represent a similar kind of situation or a continental ribbon. And this part of the basin, this V-shaped basin, is probably this inner rift basin, which is failed. Actually, there was no breakup initiated along this, but obviously, whatever that cut you can see there, it is the lateral clearance because of the transform. So that we can see the transform effect coming and cutting into this, into the older rifting system, then relatively younger transform system. So that we see their effects also. But eventually, what our focus of today is, we talk about this kind of inner rift basin which underwent some kind of extension, some strain localization, but it got aborted at some point of time.
You're at about 11 minutes now.
Yeah. So this is one of the sections. You can see that this is sections is located here. It is inner part of the stretching zone. So we can see this different stretching. But interesting thing, we can see that we can see three different detachments, as and which is this the uppermost is the oldest, whereas the younger is the lowermost is the youngest. And you can see these newer faults cut across these older detachments. That from that relationship we can understand, from that cross-cutting relationship we can assign the relative age of these detachments. But these detachments as a result of progressive cooling. So at this failed rift, each and every time the extension is happening and new detachment is formed as a result of its upliftment, its transient thermal uplift, as well as its progressive cooling. So we can see these successive detachments and we can kind of map them. This line is, if you can blow up this line, you can see these detachments are very clearly can be mappable, and it can be mapped throughout the 3D sections. But if we should go to the next features, apart from everything, first striking features is this dome. And this dome is a kind of symmetrical dome within that. And this, if you can see that this is not a horse block, and we confirm that there is no regional compression, that it's a fold, compressive fold structure. No, it is not. So whatever you can see here, this kind of rift sections, entire rift section is folded like a dome. Now, what kind of feature can create the dome? One, so compression we can rule out. One thing can be some translational event as these strike slips are coming into it. So that is one example. Another possibility could be this kind of doming as a result of the flow of the lower crust, and because the crust is so buoyant and it flowed up, it actually flows above and it formed a dome in a very, very narrow zone. We can see all kinds of rift sediments within that. You can see these older faults and we can see these successive detachments there. And we can see this kind of huge erosional boundaries on top of that. And this kind of thinning faults are gradually taking over as the time progresses. So these kind of major fault system coming gradually later, and that is what controls these domal structures, as this fault thinning related faults come into picture, and we due to the pressure difference, the lower crust getting moved away and it is buoyantly floating. So this is, I'm not saying that is an unique solution, but this is one of the plausible solution. If we go further eastboard, we see these sections. Though these sections looks quite kind of a similar what we see here. So we see this kind of thinning related fault. We can see this kind of these are the reconstructed erosional horst tops. So that we can see this, how tall it were, and we see these all kind of faults which are the later faults are taking over. So initially it doesn't look like there is a much doming effect. Okay, so here is no domal effect we can see like we see in the previous sections. But if we do some seismic flattening at two levels, one is that first one is that is the final breakup or event. So this is the Turonian event. So these sections, if we flat at this section, you can see again the dome. And if you flat even at the syn rift top level, that is kind of Aptian Albion level, you can still see the dome. But where the dome is more of centrally located and this dome is more asymmetric. So we can see that how the asymmetry is getting introduced in the system as the system is becoming progressively warmer, because as you move outboard, the systems are progressively warmer, and more strain localization focuses this kind of systems into it. And this is a cartoon that what it could have been looked like at that time of its formation. Present day, because of the rapid thermal subsidence after that and presence of this thick kind of positive sequence, the geometry looks kind of different, but this is what it looks like. So if I take one line which is something like that, this line kind of summarizes that how this complexity is there and how this buoyancy force affects a different part of the crust. So this northwestern third, it mostly stretching dominated. So we can see all kind of high angle faults, thicker rift sections over here. But what interesting, we can see as we move to the central third, it goes to that relatively mature rift section which undergoes thinning, and we can see all kind of thinning related fault. But interestingly, still we can see relatively thicker sediments, synrift sediments. So this is one of the key observation we found, which is a departure from our traditional model. So even within the thinning, within the necking or within the thinning, it is getting relatively higher subsidence and relatively higher sedimentation in this region. So as we move towards this southwestern third, this is the part of this transform system which cut across to entire rift system along this, somewhere along this, and we can see this exhumed mantle part on this side, and we can see some kind of continental holoctons floating over here also, which can be maybe transported from along this path. So you can see that if you see this basin as a whole, and if you go interpreting the different structures, you have to separate the different domains out of it. Otherwise, in a single way, these basins cannot be interpreted. So one interesting thing is that we can observe from here our detachments are quite deeper. Here our detachments are relatively shallower. So what we can see that the buoyancy forces, once it is sets in, the stretching behavior starts off and it goes on, and it is taken over mostly due to the thermal forces, and buoyancy forces controls the rift system. So if I go by the evolution of the rift system, so initial rift, we can see that it is initial rift in this basin. These are the series of cartoons we can see. So up to Torsian onwards, the initial stretching dominated rift, and then during Valanginian, when India-Antarctica breakup occurs, we can see these doming structures because of the movement of the lower crustal flow from this section towards this part. So therefore, we can see this central axial high is got is the central doming is formed, but the doming gradually becomes asymmetric during this stage, where we can see that this transform fault effects are taking place, which is gradually taking over along this margin, and continuous thermal driven uplift causes this kind of geometry. So as I told you before, that this is not a single one rift event. So there are multiple events influences the complex basin structure, and this is the final structure, post-rift structure, when we see the thermal subsidence, and this is kind of the present day geometry. So with this, I can talk about, I cannot say that we can give the entire answer to all the questions, but some learning, some understanding we can definitely take. So this is a rift evolution is not a sequential, rather it is sequence of events. It varies also laterally. It is not a single linear sequential event. And the failed rift sections are very important to understand these transitions between the stretching to necking and taking over, and gradually to the thinning where the thermal forces taking over. And we can see the successive detachments are formed, different generations of detachments are formed at different levels because of the successive cooling effect and the brittle ductile change in brittle ductile transition. The doming within failed rift is due to the dynamic uplift probably, and the progressive cooling, and or a combination of both. And in the mature part, whatever we can see, the doming is a result of mostly result of the transient uplift, because it is very important to see these kind of asymmetries getting into it because of the domal uplift, and domes are becoming asymmetric and the thermal buoyancy forces are taking over. And obviously we can see the grabens thickness from gradually thicker grabens. We can see the southwest, northwest side, and then we can see the southwest side to northeast side. So that's what we can see, observe. So these are kind of observations we can make. So with this, I end my talk. So if you have any questions, I'm open to it.
Thank you so much, Sudipta. We're really tight for time, but I think, Derek, do you have a quick question?
Yes, thanks, Sudipta, for the talk. How typical or atypical do you think this structure and breakup history is for the east side of India, for the margin?
Say again, I once more, if you can.
How typical or atypical do you think the structure you interpret and breakup history you interpret is for the margin of the east side of India?
Yeah, it is very atypical, Derek, because I think the complexities arises because of the interaction between many forces. One is rifting forces, and that is overprinted by the dextral strike slip influence. So it is very, very atypical. And I have seen similar kind of structures, but I have not worked there. Some things, observations along the southern Australian margins. But again, that cannot be on one-to-one correlations. But that proves the buoyancy, the Australian and Indian conditions, if we put together, because that work is done by another group. If we put together, we can only say that buoyancy-driven forces, we expect it is not even very late, even it can come very early into the rift evolution stages, even after very quickly after the necking starts.